Hello, good morning or good afternoon, depending on where you are connecting from. Welcome to today's webinar. So I am Carlos, I'll be your moderator today. And as you can see on the screen, today we'll have four experts talking about growth opportunities in renewables plus storage. So just before we get started, a few housekeeping announcements. So in these webinar is being recorded, so we'll send you the recording in a few days, and also the slides that our presenters will be using as visual support today. What else? So another important thing is that you can actually send questions through the Q&A box. So if it's the first time that you join us, you'll find if you run your cursor down to the bottom of the screen or at the top, depending on your configuration, you'll see a few options. One of them will be Q&A. So you can send questions through the Q&A box. And I can see already a few messages there, but we have kind of like a tradition at ATA Insights and at RenMed, which is that we ask attendees to tell us where they're joining from using the chat function. So I can see already a few people who have told us where they're joining from. So yeah, you can please feel free to introduce yourselves and let us know where you're joining from through the chat. Just so you know how this works, so we'll start with a brief round of presentations of themselves by the speakers, and then we'll have individual presentations, and after all presentations have been delivered, then we'll answer the questions that you would have sent through the Q&A box. So I think I'd like to welcome all of you and the speakers. So I'll start by asking them to introduce themselves in the order in which I see them on the screen. So I'm just going to perhaps I'll stop sharing this so you can see who we are. Hang on. There we go. So perhaps let's start with Joe. So Joachim, if you can introduce yourself briefly, please.
Hi, yeah, my name is Joachim or Joe Seel. I'm a policy researcher at the Lawrence Berkeley National Laboratory in Berkeley, California. We are one of the many national research labs primarily funded by the US Department of Energy. I work in the electricity markets and policy department and focus on wind and solar market developments, their integration of high shares of intermittent resources into the electricity grid, wholesale market valuation of renewables, and more recently, the challenges of interconnection to the bulk transmission system and delays in interconnection. Thank you for the opportunity to present today, and I look forward to an engaging conversation with you all.
Thank you very much, Joachim, for your presentation. And then I'd like to ask Caitlin to introduce If you could introduce yourself briefly, please.
Sure. My name is Caitlin Murphy, and I'm with the National Renewable Energy Laboratory, another one of the research laboratories funded by the Department of Energy. My work focuses on long-term planning for the US bulk power system and how it's influenced by evolutions such as electrification and policy drivers that influence the economics of various generation assets. Happy to be here. Thanks for this opportunity.
Thank you very much, Caitlin, and welcome to this webinar. So now, Aaroh, if you could briefly introduce yourself, please. You're on mute. Okay.
Yeah, I'm on mute. Thank you for the opportunity. My name is Aaroh Kharaya, and I'm a director of energy storage engineering at Primergy, which is a solar and energy storage developer. I'm responsible for energy storage procurement and EPC contract negotiations at Primergy, and work closely with owners, engineer, other project stakeholders to take projects from early stages to commercial operation. Also, I support a revenue assessment, project financing, and maintaining relationship with battery vendors, and just keeping pulse of the general renewable energy market here at Primergy. So again, thank you for the opportunity here to talk with everyone.
Brilliant. Thank you very much, Aaroh, and you're very welcome and we're glad to have you here today. So last in the round of presentations, but definitely not least, Sherif, if you could please introduce yourself.
Sure. So my name is Sherif Abdelrazek. I'm Director of Energy Storage and Microgrid Engineering at Duke Energy. So just for everyone's background, Duke Energy is planning for anywhere between 8 to 16 gigawatt hours of energy storage as part of our carbon plan. My team is primarily responsible for all matters technical relating to the identification and design and development of these projects.
Thank you very much, Sherif, and welcome to today's webinar. So without further ado, I'll open the floor to Joachim Seel from Berkeley National Lab to start the round of presentations. Yeah, I can see your presentation, so it's on full screen. So over to you.
Thanks. Yeah, just had to unmute myself. So thanks again for the opportunity to present today. Today, I'll just showcase some of Berkeley Lab's recent research papers. Our research is intended to support private and public sector decision-making about hybrid projects in the United States. And we analyze the where and the why hybrids are being built. We've modeled optimal hybrid design choices and assessed the contribution of hybrids to resource adequacy and short-term reliability. And we've evaluated how hybrids can participate in wholesale power markets and investigate as well the cost and the value both of customer-sided but also utility-scale hybrids. And today I'll only share a few tidbits given the constrained time. But these are all just excerpts of larger and longer research papers, all of which are freely accessible on our website. So I think it is well known that the 2010s really was the decade in which wind and solar growth really took off in the United States. And I think in the 2020s now we're at the cusp of an enormous growth wave of hybrids, hybridizing those previously standalone storage and to a lesser extent wind assets. On the left side here, I have an excerpt of our annual utility scale solar market report, where in blue you can see PV standalone projects and how they've steadily kind of grown over the past decade. Starting in 2021, really, we saw for the first time a large amount of new projects that were designed from the very start as hybrids, as well as some retrofits of older standalone PV projects that now gained a storage asset with it. And so by the end of 2022, in the United States, we have about 6.5 gigawatts of utility scale PV that's larger than 5 megawatts, with more than 3.5 gigawatts of storage capacity or 10 gigawatt hours of energy capacity. But if we look into the future, we can really see an enormous amount of low carbon resources that developers want to bring to the grid. We've analyzed all the capacity that is waiting in the nation's interconnection queue in order to get to access to the transmission system. There are nearly 2 terawatts of low carbon resources in there. Nearly 1 terawatt of solar is in those interconnection queues, and about half of that, 460 gigawatts or so, is proposed to be a PV hybrid. And you can see that at the bottom here in the blue graph, that's storage. About half of the proposed storage capacity as well is supposed to be hybridized, meaning it's supposed to be co-located with a solar asset. Now, not all of that will be built. Currently, we have about 1 terawatt of load in the United States. And historically, we've seen completion rates of a little less than 20% of the capacity that is waiting in the queues. But it's just an enormous amount of developer interest out there. So if we would be able to unlock that, we would make significant strides in meeting decarbonization goals here in this country. There have been, as I mentioned already, some projects, some hybrids have been deployed, and we can look at their configuration in order to get some insights on what design choices are popular. And we can also look at power purchase agreements, or PPAs, which usually lead the market by a few years before a project becomes commercially operational. And what we've seen here is that the general price of these solar hybrid PPAs has fallen over the past few years. In Hawaii, they're a little bit more expensive because everything is a little bit more expensive in Hawaii, but also because the storage assets are larger there, given relative to the PV capacity, about 100% or so. In the last year or two, actually, we've seen a little bit of an uptick in the levelized adder that the storage asset kind of brings to the hybrid. Now it's about $15 a megawatt hour or so for PV generation. And that is in part due to the growth in the relative size of the storage asset relative to the PV capacity. So about half of the capacity now. So if you have a 100 megawatt solar project, about 50 megawatt storage asset or so is now usually paired with that. We've looked at historical wholesale market prices and tried to estimate what the wholesale market value of the addition of the storage asset would be. And in this instance, what I'm referring to here, we used prices up to the year 2020, and we found that the net value of hybridization appears to be positive, at least in some regions back then. So you can see the difference between the PV standalone and then the 2 PV plus storage bars in CAISO and ERCOT of about $13 to $22 or so per megawatt hour. And if you compare that to the storage adder of about $15 a megawatt hour that I just mentioned, you see that we have a positive net value here. Now, these were historical wholesale market prices. I think you all know that the wholesale market environment changed quite a bit in the year 2022 with rising natural gas prices and rising wholesale electricity power prices. And so I think the economics have shifted even further in favor of hybridization. We're currently in the process of updating our analysis, so stay tuned to that. We have developed a fairly simple battery degradation model to compare the revenues and cost of different hybrid designs. And we've found quite a bit of variation in value by configuration and also region. So you can see here that in CAISO, the net value is kind of the most positive, whereas in New York ISO, for example, the net value appears to be quite negative across all the design choices that we've looked at, especially as you go to longer duration storage assets. Those are naturally more expensive, and that doesn't seem to come with the same degree of increase in revenue. So the net value is the most positive at the moment with short duration batteries of 1 to 4 hours, kind of what we see in the market. Now that may change in the future, and I think Caitlin will talk a little bit about that going forward. I'd like to briefly mention ancillary service markets and revenue opportunities there. At the moment, standalone solar or wind assets have a hard time in the United States to participate in those ancillary service markets, whereas hybridized solar or wind assets have a little bit of an easier avenue there. And we find that in some regions, there are quite large revenue potentials of more than $30 per megawatt hour of additional revenue that one could unlock if one was able to participate in those markets. But these markets are relatively small, especially when compared to the enormous amount of hybrids that are currently waiting in the queue. And so once these thin markets become saturated, of course, the prices will decline and revenue opportunities will decrease. And so like banking only on those ancillary service market revenues, maybe a little bit of a risky strategy. But for the moment, there's still quite a few bucks to be made there. I want to conclude by touching briefly on different business models of how one may choose to operate the PV hybrid asset. Because actually, when we looked at many of the projects that were operational already in the year 2020, 2021, we found that the majority of them did not try to participate directly in the wholesale electricity markets, but instead try to reduce apparent load of utilities, for example, when it comes to assessing their contribution to the financing of the transmission system. And that's what we call the peak load reducer model. Or they try to participate in special incentive programs. For example, in ICE New England and Massachusetts, there's the Massachusetts SMART program that has very distinct requirements of how you have to dispatch your storage asset in order to comply with the program. And we've shown here at the bottom how these projects operate empirically and how they would operate at the top if they would follow directly wholesale market signals. And you can see that if they would follow directly wholesale market signals, they would dispatch much more frequently. Whereas if you just try to reduce your peak apparent load that is assessed at 1 hour per month, you maybe dispatch 5 times or so a month because you don't quite know when you'll have your peak load hour. Whereas if you would follow the wholesale market signals, you would dispatch much more frequently. Now, why would you do that? Well, we looked at the revenue opportunities by these different business models and found that at least for the moment, some of these business models are really, really rich, and you can earn higher storage premiums or higher total revenue via these alternative business models than with a strict merchant model where you just follow the wholesale market. But especially as the deployment of hybrids increase, I think it becomes increasingly important to align those incentive structures with actual wholesale market signals to ensure that we really squeeze the most societal value out of these hybrid assets. And with that, I want to conclude. If you have any questions, feel free to contact me. Again, this is just a very small excerpt of a much broader research body, and a lot of the underlying reports are mentioned in this synthesis paper. I'll drop a link to that in the chat box. So thank you very much.
Thank you very much, Joe, for your insightful presentation. So I'd like to remind everyone at the audience that they can you can send questions through the Q&A box, and we'll get to them after all presentations have been delivered. So now I would like to give the floor to our next speaker, who is Sherif. So Sherif, whenever you are ready, you can start sharing your screen. I think, Joe, you need to stop sharing yours so Sherif can. Yeah. Thank you.
All right. So let me know as soon as you are able to see my screen here.
Yeah, it's loading now. So yeah, I can see your screen, although it's not on full screen. I can see other things here. Maybe go to full screen mode.
There we go.
There we go. Perfect. So over to you, Sherif.
Perfect. All right. Thank you so much. So just a brief introduction about Duke Energy and kind of what we're doing currently. So Duke Energy is a vertically integrated utility that operates in 6 different states: North Carolina, South Carolina, Indiana, Ohio, Kentucky, and Florida as well. I think the most relevant thing to mention here is that we are expanding very heavily on both solar and solar plus storage projects. So over, like I alluded to earlier, over the next 10 to 15 years, we have 8 to 16 gigawatt hours of energy storage systems planned. Some of them are standalone, some of them are tied with solar facilities. So for myself and my team, we have a very interesting problem to work on. We have this massive grid, and we have certain targets for deployment of energy storage. So the awesome problem is, all right, where do you site these batteries electrically on the grid to create the most value? And also, how do you design these systems to make them the most cost effective for our ratepayers? All right, so for this presentation, I wanted to go over just the different architectures that are out there for solar plus storage systems. Each one has its own characteristics and its own use cases. So I just wanted at first to go over these architectures and then talk about the characteristics of each one, round trip efficiency and just different complexity levels, and then talk a bit about clipped energy storage harvesting. So for this slide, and I'm not sure if you guys can see the full slide, or if the it's blocked by the on the right here. But
I can see the full slide.
Perfect. All right. So in regard to the architectures that are available for solar plus storage systems, they can mainly be categorized into 2 buckets, basically. One AC coupled and the other DC coupled. So for AC coupled systems, as the name implies, the battery system is tied to the solar system on the AC side. And depending on where that tying occurs, it could either be medium voltage coupled or low voltage coupled. So for medium voltage coupled, that basically implies that for transmission tied systems, you're kind of tying your battery systems between the project's GSU and the PCS, or the power conversion station transformer. So both the solar and the battery system has their own respective medium voltage transformers, and in addition to, of course, their own inverter. Now, for low voltage coupled systems, this is an architecture that is offered by some inverter manufacturers out there, where they basically put 2 inverters on a common skid, and both of them are connected to the same medium voltage transformer. So that way, when you're charging from solar directly, you're not going through the medium voltage transformer, both on the charging side and then the discharging side. So, which is a differentiator from the medium voltage coupled architecture. Now, shifting to kind of the lower half of the screen here, for DC coupled systems, they can mainly be categorized into 2 architectures. One, sole solar charging, which basically implies that you can only charge your battery system from your solar DC array, but you cannot charge it from the grid, since this is a for the most part in this architecture, a solar inverter that is unidirectional. So I think this architecture is more common in retrofits. And I think there are some inverters out there that are, even for retrofits, they, with a firmware upgrade, they can be converted into a bidirectional inverter, which can allow charging from the grid. But for the most part, it's retrofits are kind of almost always unidirectional. Now, for bidirectional or flexible charging architecture, the inverter is bidirectional here, and effectively allowing you to charge from the grid, to the battery system. And like I said, this is more kind of common in new systems because you're planning from the start for to have both solar and storage, and you're going to charge the storage, and if you're in a market, you want to have that flexibility to be able to participate in services if the sun isn't shining. So you want to be able to charge from the grid to enable yourself to do that. So you kind of design the system from the front end to have a bidirectional solar inverter. And like I said, there's a number of inverter OEMs that offer this feature with just a firmware upgrade, but others that simply do not offer it because they're the hardware within the inverters themselves do not allow for bidirectional operation. Now, I wanted to kind of brief over the different characteristics of these architectures. So at first I'll talk about AC coupled systems. In terms of maturity, they're both really, really mature. Control wise, we're executing these two topologies do not have really any complications coordinating between the battery inverter controller, the solar inverter controller. No issues there for the most part. There's a lot of experience in the industry on these two architectures. They enable you to perform grid ancillary services, since really you have a dedicated inverter for your battery system. You're almost totally decoupled from your solar resource, especially if your interconnection allows for both to operate at the same time. But then on the efficiency side of things, you get a little bit higher efficiency from low voltage coupled systems, because you kind of avoid, as opposed to medium voltage coupled systems, you avoid that additional step of going through the medium voltage PV transformer to the medium voltage energy storage transformer and then discharging back to the grid. So here you're kind of going solar, then inverter, then another inverter, then to the battery, then battery, inverter, one medium voltage transformer. So that's where you get a little bit higher efficiency for solar energy dispatch to the grid. Now, for DC coupled systems, the two different architectures we talked about here, I think the common thing between them is that they are still somewhat developing. There's a lot of kind of strides being made, advancements being made, kind of DC-DC converter manufacturers working together with solar inverter manufacturers on common controllers, so that, as a project owner, you don't have to worry about the integration between, the inverter and the DC-DC converter, which could get really, really complicated. So that's advancing, but I think at this stage where we are today, it's still developing. Like I said, for control complexity, this second column here is control complexity here. It's a little bit more challenging with flexible charging because, there's just an additional mode of operation where you're able to charge from the grid. So that could get a little bit more complex and just make the integration a little bit tougher. In regard to use cases, so both are really good in that they allow you to capture clipped energy or energy from the solar facility that would otherwise be clipped and wasted. So, especially for high inverter overbuild ratio or solar DC AC ratio, the higher that value is, the more energy that you can actually increase coming out of the project. Now, on the efficiency side, kind of contrary to just common belief, I'll just call it. Actually, both are somewhat less in terms of efficiency compared to AC coupled systems, especially for low voltage AC coupled systems. And that's mainly because DC-DC converters, for the most part, have a little bit higher or a little bit less efficiency than inverters. That's why it's a little bit more taxing to go 2 times through a DC-DC converter versus going through an inverter. Now, last thing I'll mention, kind of in regard to that application that a lot of developers are targeting to increase the overall production from solar plus storage facilities by coupling batteries on the DC side. We ran this study for a 2-hour battery system and a 4-hour battery system that would be sited in Florida with a solar facility. So on the x-axis here is the DC-AC ratio of the solar facility. On the y-axis is the percentage increase in total energy production from the facility. And these different curves represent different power capacities of the battery system related to the solar system. So if if one of these curves was 50%, and we're talking about 100 megawatt solar project, that would represent a 50 megawatt battery project. And since it's 2 hours, it would be a 100 megawatt hour system. So you can see here, kind of as the DC-AC ratio or the overbuild ratio of the solar facility increases, there's a linear zone in which you get additional energy production, especially the higher the capacity of your battery system, which means, obviously higher capability to capture clipped energy. But then, for each of these curves, you get to a point where you start to see diminishing returns. So then kind of your optimal region becomes, in this inflection point here. Now, once you go to 4-hour systems, that obviously increases the overall energy production and, the overall additional energy you can harvest from solar facilities. But still, since I think that the biggest takeaway that I wanted to convey from these 2 charts here is that really, unless your DC-AC ratio, or also called your inverter overbuild ratio, is kind of higher, it really doesn't make sense to focus on capturing clipped energy, because there isn't that much additional energy to harvest with solar with lower DC-AC ratios. So there's a lot of solar facilities out there at a 1.3, 1.35, and 1.2. So if you're thinking about retrofitting those and trying to harvest clipped energy, really it's not going to be that effective. You're under really 2.5% in both cases here. But definitely for higher DC-AC ratios, there's an opportunity there. Also makes a difference if it's a retrofit, or if it's a net new facility and you're designing it so you have that flexibility for all these design parameters. So that's when I think you can optimize both your solar facility DC AC ratio in addition to the sizing of the battery system you're planning. All right, sorry to go a little bit over there, but that is what I wanted to cover.
Thank you very much, Sherif, for your presentation. There are a couple of questions in the Q&A box already, but we'll get to those after we are done with all the presentations. So now I'd like to give the floor to Aaroh to deliver his presentation. So Sherif, if you can stop sharing, I think you need to do that so Aaroh can share his screen as well.
I did pause. All right, there we go. Stop sharing.
Yeah. And whilst Aaroh is finding his presentation, sharing his screen, I'd like to remind all of you that yes, we'll send you a link where you'll be able to get all of the slides and the video recording. So over to you, Aaroh.
Could you confirm if my slides are visible?
Yeah, I can see your slides and they are on full screen, so I think you're good to go. Perfect.
And again, thank you everybody for the opportunity to present today. Just to reintroduce myself, I'm Aaroh Kharaya. I'm Director of Energy Storage Engineering at Primergy Solar, which is a independent power producer. And we do solar and energy storage projects across the United States. Here are the topics for today. I'm going to quickly talk about Primergy a little bit, and then focus on specific growth and trends on battery system integrators, battery products, and non-lithium technology. Right, so for a quick introduction to the company, Primergy Solar was founded in 2020 and is headquartered in Oakland, California, and I'm based out of Memphis, Tennessee. Primergy Solar is a portfolio company of Quinbrook Infrastructure Partners and represent Quinbrook's principal solar and energy storage investment platform in North America. At Primergy Solar, we specialize in solar and energy storage projects, development, ownership, and operation. We have a growing pipeline of solar and solar plus energy storage projects, which is 8.2 gigawatts for solar and 6.6 gigawatt for battery energy storage in development. And a quick segue to what Sherif has talked about. We are working on what I believe is one of the largest DC coupled energy storage project, which is our marquee project called Gemini Solar in the last 35 miles outside of Las Vegas, Nevada. This project is 690 solar and 1.4 gigawatt hour of energy storage system. Like I said, by far it's one of the largest DC coupled projects in the United States, probably in the world. About 1.8 million modules spread across 5,000 acres of site with a 25-year PPA, and the plant is large enough to cater to about 150,000 homes, and it also has about more than 4,000 battery enclosures. So this wraps up the quick introduction to myself and the company I work for, and I can now dive to the growth and trends of battery system integrators. I've prepared a few slides to talk some specific items that I wanted to cover today. So according to IHS Markit, the integrator installation is expected to triple from 2020 to 2025 and reach 15.1 gigawatts. There are three main types of a battery system integrator services provider. There are full stack services provider like Tesla, Fluence, Wärtsilä, which provide a fully integrated solution all of from battery to inverters and the software solution. And then there are light integrators like Doosan and iCha and SunGrid and other EPCs, which will use owner procured batteries and provide inverters and integrated for the owner, and obviously provide some level of performance guarantees around it. And finally, there are asset monetizers like STEM, who typically deploy software on top of an integrated battery system to maximize the value of energy storage system. The energy storage market is incredibly dynamic. So this is a snapshot in time. There's definitely a movement happening always in actually probably changes quarter by quarter for some of these companies and how they are looking at the growth in energy storage market. However, there are very clear trends that one can identify when we look at the market from a high level and start to dive down a little bit. I think there are three major trends. One is everyone is intending to move deeper into the value chain. So a system integrator would want to get deeper into rack and module design, or a battery OEM, which I'm going to discuss next, is going to move up the value chain to provide integrated solution. The second key trend is providing additional services offering to differentiate capabilities with the competitors. So a lot of this has to do with data analytics, predictive maintenance, machine learning, and possibly AI to be able to differentiate between X, Y, or Z integrator. And finally, which is a very nascent trend right now, is establishing joint ventures with battery manufacturers directly. So going to the source and trying to establish strategic relationships with battery vendors and providing and integrating their products all the way through the spine of the products that you're selling out in the market. A primary example would be Fluence signing up a deal with Northvolt, and this is about a year ago. So again, very dynamic situation in the market. Now I want to talk a little bit about controls here as well, as I don't feel I'll do justice if I don't talk about it. So the diagram here kind of shows how I look at battery system integration and how I categorize it myself. So as you can see, while the control system initially provides only elementary functional controls, right, to make the system safe and provide just functional monitoring, additional services are being offered to enhance the value of the system. And those additional services are operations and maintenance, augmentation scheduling, asset management, and also performance monitoring. And the integrators are definitely moving into space and out of the space to provide other functionalities and build upon the capabilities that they already have. Next one. So this is another segue into what I was talking about earlier, about everyone trying to expand the reach in the market as this is rapidly growing. So one of the key examples here that you can see is battery OEMs are continually moving up the value chain. Right now, as owners, we are able to find fully packaged DC blocks from battery OEMs, which we were not able to do, let's say, in 2018 or 2019. The only way to do that was to go through a system integrator. And when I say DC block, I define DC block as a battery rack that is in an unoccupied enclosure integrated with battery management system, thermal, as well as fire protection system. And these DC blocks come with their own product specification, warranties, and degradation curve. So a simple analogy in that I can give is of modules in PV, like modules. They come in a self-contained unit, and they are warranted to a certain specification by the OEM. Same is true for the battery and the DC blocks that I was talking about. Almost all battery OEMs are doing this. And so to take some prominent examples would be CATL, LG Energy Solutions, Goshen, and SYL in the market. And the next one that I want to specifically talk about, and again, there can be a whole presentation on this topic, but I've distilled it to suit the time here, is the growth and investment in non-lithium technology, which again, as many of the listeners would know, that is a clear trend. I'm sure everybody has read news over the last 2 years about investment in this non-lithium battery technology or that. So I definitely see a significant growth and a clear trend in this. If you look at Wood Mackenzie analysis, over $58 billion have been invested in non-lithium technology so far. And there are very variety of reasons why there is an interest in non-lithium technologies. And they are essentially supply chain challenges and bottlenecks that we all went through and probably are still going through in many cases for the projects that were traditionally lithium ion. The rise in prices of batteries just because of rise in prices of lithium hydroxide and lithium carbonate, which are basic raw input materials in production of lithium ion batteries. And finally, the use cases are evolving as well. As you know, utilities are moving increasingly and will eventually move increasingly towards greater than 4 hours duration storage, which can be broadly defined as long duration storage. And there are multiple non-lithium companies like Ambri and Renew, Farm Energy at various stages of product development and deployment. The latest example that I can share with the group here would be Renew, which will build up to a $1 billion manufacturing plant in Kentucky, which was announced a couple of weeks back. Obviously, a lot of this also has to do with, for non-lithium battery technology, has to do with Inflation Reduction Act, which provides assistance to build and scale advanced battery chemistries and manufacturing in the United States. So as project owner and project developer, we at Primergy are really excited about some of the developments that are happening here, and definitely look forward to and keenly engage in the market to see where the growth and trends are going for reliability and manufacturing skill to achieve, so that we can deploy such technologies on our projects when the use cases evolve and they suit our need. With that, I'll stop here and pass on the baton back to Carlos and probably then to Caitlin.
Thank you very much, Aaroh, for your presentation. So now, in the interest of time, I will give the floor to Caitlin. So Caitlin, please start sharing your screen whenever you want and start your presentation.
Hey, is that coming through okay?
It's coming through okay. It's on full screen, so over to you.
Great. All right, thank you again for this opportunity. I'm the final panelist, and I just wanted to round out all the information that we've heard and learned about today by looking at the growth opportunities in terms of the market growth potential for these types of technologies. So within the context of the demonstrated industry interest today in generation plus storage systems, and thinking about all the technical advantages that were presented by Aaroh and Sherif, what could this mean in terms of the total market size and deployment potential for these types of systems? So the focus is mainly on PV plus battery systems, because those are the ones that we see most commonly in the interconnection queues. But I'll briefly touch at the end on some sort of more future opportunities in terms of where these synergies could be captured with different technology combinations. So just one slide on background to kind of put all of this in the context of what we see as the growth potential for energy storage technologies on the US bulk power system in general. So we have a variety of sort of long-term planning studies looking at the evolution of the US grid, trying to understand what we think will be deployed over future years, what we want to be prepared for, both from a siting perspective, but also from a regulatory and markets and policy perspective. So across all of our scenarios, we do see a growing role for energy storage going into the future. The plot in the bottom right is maybe the best demonstration of this, looking at the evolution of energy storage over time as the grid continues to evolve. So in the near term, we see a really prominent role for some of the shorter duration technologies, similar to what Joe had presented early in this presentation. But going into the future, we see an evolution where longer duration storage technologies start to become more competitive and provide more value to the grid. This is especially true and important if we start to run into growing challenges related to transmission siting, because storage is a nice way for us to avoid the need for large transmission expansion by getting more output from each individual renewable plant, rather than having to interconnect lots of smaller plants across the country and then balance those together. So this is also part of the explanation for why we see a lot of potential growth in the hybrid system space, because by combining renewables and storage together, you can really spread out the amount of time those plants are producing generation for the grid by being able to control them and also being able to capture some of that clipped energy that Sherif was talking about in the DC coupled systems. So as I said, the focus of my presentation is really on looking at the economics and then deployment potential for storage-based hybrids. This is based on some modeling that we have, sort of our flagship model at the National Renewable Energy Laboratory for long-term grid planning. So this is the REEDS model, which is a capacity expansion model similar to sort of an IRP-based tool, looking at all the various resources that can meet the needs of electricity customers and trying to figure out what portfolio can meet all of those requirements at least cost. So taking kind of a system operator, system planner perspective. I won't go into detail on this slide, but just wanted to highlight that a lot of the benefits that Sherif walked through in terms of especially the DC coupled systems, that's really what we're representing in our model. So we do represent the ability to capture clipped energy. We represent the higher efficiency associated with coupling PV and storage together. So not necessarily comparing AC coupled and DC coupled systems in this case, but thinking more about what it would take to generate PV at one point, transmit it to storage somewhere else, and then send that to a customer. That's the efficiency I'm referring to here in terms of a higher efficiency of utilizing the PV from a given site. We also captured the potential for cost savings associated with siting these technologies together. So it's not just on the value side of the equation, but also on the cost side. If you are planning and building these things together, then we expect to see a relatively small but not insignificant reduction in the total costs of deploying these systems, because you can have shared inverter technologies as Sherif presented, but also shared balance of system costs when you're siting these technologies together and deploying them together. And then finally, there's also the potential for curtailment benefits by avoiding a situation where your renewables are kind of stuck where they are because of transmission congestion. If you have co-located storage, then you can use that to try to recover generation that otherwise would have been wasted. So taking into account all of these potential benefits of hybridization, we can look at some long-term planning scenarios and try to understand what the growth potential is for coupling these systems together. And the way we try to isolate that potential for hybridization is to first run a scenario that just looks at how does the grid evolve if hybrids didn't exist at all? And that's what's shown here on the left scenario. So we are, this does include a very aggressive decarbonization trajectory for the United States bulk power system. And under those conditions, we see a dramatic expansion of solar technologies, wind technologies, and storage technologies. So this is all just pointing to the fact that those are the least cost resources that don't produce any carbon emissions, and therefore they become part of our optimal scenario when we don't have hybrids as an option. If we then introduce to the model the option to put these systems together, what we see is sort of direct competition between the hybrid technologies, which is this beige color above the zero axis here, competition between these hybrid technologies and then the separate PV and storage technologies. So the main point here is just to say, when we introduce hybrid systems, we don't see that that necessarily facilitates additional solar deployment or additional storage deployment. Instead, what we see is that the system really values the ability to put them together to both realize those cost savings, but also the efficiency benefits. So from a system perspective, it really makes the evolution simpler, even if it isn't changing the total mix of how much solar is providing to a decarbonized grid, for example. If we look at this on the storage side of things, it's a very similar story. So the comparison of these two bars here is just showing what happens when hybrids are not available as an investment option and what happens when they are. Ultimately, that actually leads to less overall battery deployment here on a gigawatt hour basis. But that's because we're using these assets more efficiently. We're using them more, we're cycling them more because of these synergies between the generation and storage technologies when we put them together. As I alluded to earlier in the presentation too, the other main advantage of being able to couple these systems together is really when you think about the trade-offs with transmission expansion. So this is one of the main benefits we see in our modeling, that putting solar and storage together in one location avoids the need for some of the transmission expansion that would be required otherwise. And this is especially pronounced when you think about scenarios that involve aggressive decarbonization of the power system. So the details will vary scenario to scenario, but ultimately the difference between this dashed line and the solid line is the benefit of hybridization in terms of avoiding the need for additional long distance transmission, which in the United States can be really hard to build and to realize. So this is probably the most important benefit of these types of systems, especially now that the tax credit incentive for coupling is not as strong as it used to be prior to the Inflation Reduction Act. And overall, this translates to the ability to reach decarbonization goals at a lower total investment and operational cost. Again, primarily rooted in the ability to avoid the long distance transmission expansion. So the final point I wanted to make is just, we talked a little bit about the different configuration options that are available if you're looking at coupled systems. And Sherif had the nice plot at the end of his presentation about sort of the optimal storage sizing for a given amount of PV. We similarly see that, for smaller DC to AC ratios or for less oversizing of your PV, a relatively small battery is sufficient to get the benefits that you would want from an operational perspective. So filling in some of these gaps, making sure that solar is available at the true interconnection capacity, especially during some of these high value periods, which also correspond to high risk on the power system. But the amount of storage that you need can also be reduced by just reducing the variability in your generation source overall. So the bottom chart here shows an example of what it would look like to have PV and wind located at the same site, especially in regions where the wind tends to be stronger at night, for example. So in this case, you can realize similar value with a smaller battery because ultimately you already have a lot of generation available over the course of the day because of this complementarity between local wind and solar resources. And this is somewhat site dependent, but we do find that it's the case throughout much of the United States that PV and wind tend to generate at different times of day. So by taking advantage of both of those low cost generation sources, you can actually get similar value with a smaller battery size in that case. So just to recap kind of the key findings of this study and some of the other work that we have in this space, we do see that one of the primary benefits of renewable generation and storage combinations at a single site and through hybridization can really help us achieve our decarbonization goals with lower transmission and lower system costs or investment needs overall, which can really just help alleviate some of the challenges associated with this transition. We also see that when we do put these sites together, the local battery does tend to charge mostly from the local resource, even if it has the ability to charge from the grid, which again makes for a sort of a more efficient utilization of the solar resource or the wind resource, depending on the case. The highest value configuration will evolve over time. I didn't talk very much about that, but we do see increasing value in oversizing the PV more and more over time and moving to larger batteries. So again, another evolution, just as the system tends to evolve, we will see a change in what the highest value hybrid configuration looks like. And then of course, the Inflation Reduction Act has changed almost everything when it comes to the economics of renewable generation assets in the United States. And this is especially true for hybrid systems because storage no longer needs to be coupled to PV to receive that investment tax credit. So I would say it's kind of to be determined what happens with the competitiveness of hybrids going forward now that storage really does have this tax advantage, regardless of how it's deployed. So thanks very much. That's all I wanted to cover today.
Thank you very much, Caitlin, for your presentation. So it was very insightful. So I think, well, we've pretty much, used on the entire hour, but I think it'd be worth actually answering a couple of questions, of the questions that came through on the Q&A box. There is one here that I think it's quite interesting. It's probably aimed at Sherif, and it says it's by Vanessa Vita, and it says something like, "It was my understanding that the vast majority of retrofits are AC coupled, not DC coupled, due to complexity of those systems. Wouldn't it be easier to add on storage assets in the AC coupled fashion after a solar system is already in operation?" So what is easiest? And I don't know, Sherif, you can begin, and then the others could pile in as well.
Yeah, absolutely. Good question. Yeah, I do agree. Kind of in execution, the easier route to go for retrofits would probably be AC coupling. You're not going to be distributed across a very large PV facility. You're going to have all your battery enclosures, your inverters in one location. Just pull up, some cable and then tie there. It would be more complicated for DC coupled systems. You need to add a DC-DC converter at each solar PCS, but it really depends on what you're trying to do, your use case. So if the project you're trying to retrofit had a higher DC-AC ratio, moreover, if it was a a single axis tracking system, that would contribute to really being able to capture more clipped energy. So then it would shift things towards DC coupling, and then maybe it is worth the trouble, or worth going through the troubles associated with DC coupling. But definitely, if everything else is the same and you don't have really much energy that is being clipped to begin with, then yeah, definitely it's an easy decision to couple on the AC side. So at the end, just depends on what you're trying to do, really.
If I can add as well, oh, sorry, Carlos, I think you're muted, but one other note is I think it also depends on sort of the regulatory perspective. I know that we've talked to developers who see a lot of value in DC coupling in the sense that if you cannot, physically cannot violate your interconnection agreement limit, then that makes it easier to add the storage in the first place. So not a technical decision in that case, but maybe just avoiding regulatory challenges otherwise. But otherwise, I totally agree with the feedback and Sherif's answer that it might not be the best choice from a technical perspective, but maybe it's the path of less resistance.
Yeah, good point.
Thank you, Caitlin and Sherif. Aaroh, I don't know if you'd like to add to this question.
I'll just echo the sentiment here. As developer, path of least resistance for us is sometimes better than what is technically easy, and I'll stop at that.
Yeah,
just adding some developers inside here.
Fair enough. I think there are a few questions here that make me think that it's not clear to some people whether coupling in DC or AC impacts on the types of services you can provide. So does it have an impact on the kind of services you can provide, and how?
Absolutely. So with the vast majority of DC coupled systems, unless you got lucky like Duke Energy did with one of our projects in Florida, where we had SMA inverters that could be very easily retrofitted to allow bidirectional operation. So unless you're in that lucky case, you won't be able to charge your DC coupled batteries from the grid, which really puts you at the mercy of your solar facility production, and in terms of how often you can participate and bid your batteries in a service. So you'd be looking at the weather forecasts much more frequently for that matter. So yeah, definitely an effect there on the ability to participate in ancillary services.
You're right. Thank you. Anyone else would like to add to this question? No? Okay. And then I think, yeah, we'll answer one more question. So one of them is, do you think that the ramp rate control service in PV plus battery energy storage systems will increase over time?
I've seen some attempts at different utilities offering incentives to for combined PV plus battery facilities to limit ramp rate or otherwise known as kind of PV intermittency or so a couple of years ago, Duke Energy proposed a solar intermittency mitigation charge, or it was basically a charge that you would be paying on your solar facility if a certain index related to the intermittency of PV was higher. And when you did your homework and started to kind of design your system to smooth out that PV power intermittency, you kind of be able to deduce how much you reduce that index, and in other words, how much you would be able to reduce the charge you'd be paying for providing non-intermittent power. In the second tranche of the competitive procurement of renewable energy, it's not the current one, but that's what I know. I'm not aware of any other incentives, but it's definitely a service that batteries are really good at, is coupled with PV facilities firming PV power. That is.
Thank you very much, Sherif. And I think let's answer the very final question. I know, Aaroh, that you need to leave, so thank you very much for joining. There is one question about the how do you see the growth of interest in pumped storage in relation to batteries? I think that speaks for all of the other technologies, right, that are not just batteries. So which technologies do you see sort of like gaining traction as we have more solar and more wind, and in theory we should have more storage as well, as we have more variable renewables connected to the grid?
I'll take a stab at that one, because Duke Energy, we've been reviewing and vetting a lot of so-called long duration technologies. It's really hard, and it's a really detailed process to identify the real deals, for lack of a better term, from really the technologies that won't advance, because it is dependent on your use case. So how do you plan to use these systems? But at a high level, what I will have to mention here is that, to begin with, you have to really have a silver bullet for the technology you're vetting. A silver bullet over lithium, that is, has to be either much improved round trip efficiency, much improved cycle life, really anything that is far better than lithium to really start the conversation. Like I said, we vetted a lot of technologies. Some of them, their silver bullet is that, well, it's better from a fire safety perspective. That's the only advantage. It's much more expensive, less round trip efficiency. Really, it won't, in my opinion, this is my opinion, not that of Duke Energy, but really, if that's your only advantage, is that you don't have a thermal runaway characteristic, then it's probably not going to make it, because we all have lithium batteries in our pocket. we can deal with, thermal runaway. We're going to get better at it as an industry. So I think we're going to advance there. But if you have, if your silver bullet is 10 times the cycle life, okay, then let's start talking, right? Aaroh's kind of mentioned Venue today. That is definitely one technology that I'm very excited about. It's rated at, they'll guarantee their cycle life to 20,000 cycles. The degradation per cycle is much less than lithium. So I'm really excited about that technology. I think it'll be great for stationary energy storage systems.
Thank you very much, Sherif. So, Joe, unless you want to add to this, then we'll close the webinar now. I think Caitlin sent me a note that she had to run as well to another meeting. So,
yeah, thanks. No, I don't have much to add. I think like the only other thing on the horizon that vaguely serves a similar function is potentially hydrogen manufacturing on site, a different storage medium, which at the moment seems to have very rich incentives with the Inflation Reduction Act. So the project economics would have shifted with those new incentives available, but obviously that's a whole different beast. So
yeah, brilliant.
Thank you very much.
Thank you very much, Joe, Sherif, and of course to Aaroh and to Caitlin in absentia, and we'll and to everyone who's been with us here at the audience. So we'll have quite a few of these webinars, and actually we have an event coming up in Las Vegas in July 12th and 13th, where we'll be talking about all things energy storage. So so yeah, you can check it out on our webpage. Is that you see on the chat now. We'll definitely send you the recording and the presentation, so in the next few days. So thank you very much for being with us today, and I'll see you next time.